All right, hello everybody. So we're going to be looking at geometric and telescoping series today. So in the previous lecture, we learned what a series was and when it converged, sort of. Here's what we know so far. So we know that a series can be written like this. This is just one of them. It doesn't have to start at n equals 1. It doesn't have to finish at infinity. But there you go. That's a series. And we learned that there was a definition of convergence where we said we can define the partial sums as follows. Define the partial sums as like S, I'll say capital N, is the sum from little n goes from 1 to capital N of an, and then we say a series, nope, not series, sorry, hold on. We say a series converges if the limit as n goes to infinity of Sn equals L, and if it does, if so, then we say the series n equals 1 from infinity of an equals L. All right, and so that's the definition. And if it doesn't converge, then it diverge. If a series does not converge to a limit, it diverges. All right, so that's a brief summary of what we know. Now, what we're going to do in this section is look at two different series, the geometric and telescoping series, and learn what their limits are, if they have them. Most series, you can't actually come up with a limit. You can figure out if it converges or diverges, but you don't know what it actually converges to. But these two are exceptions, okay? So geometric and telescoping are two types of series where we can know the limit. And that's why we're looking at them. Okay, so we'll look at telescoping first. Telescoping. All right, and they're called telescoping because people think that it's like a telescope, like a pirate telescope. So like, what's a pirate telescope look like? So you got like an eyepiece, and then you got like a little tube, then you got another tube, then you got another tube, then you got another tube. There's probably enough tubes, right? And then like the lens is here on the end. Like that's like a telescope, and if you push it in, then it collapses and you just see I don't know what I'm drawing now. But it looks, it collapses down basically into a smaller thing. So it collapses down. Okay, so that's why it's called a telescoping series. Now, what does it look like? Well, what a telescoping series looks like is a lot of things. Here's an example. Let's see. I'm just going to say find the limit. Find the limit. That doesn't say limit. Find the limit of the convergent series. So I'm even going to tell you it converges. I hope I'm right. Find the limit of the convergent series. N goes from 1 to infinity of, what am I going to do? I'm going to go 3 over n minus 3 over n plus 1. There you go. Did it. Okay. Now, what you would do to find the limit of this series is you just start writing partial sums. This is one where there's no trick to it. For a geometric series, sorry, for a telescoping series, there's no trick to it. You just write sums. So write out partial sums. Starting at the first one. So S1, right, that's going to be, I'm not going to keep doing this, but like S1 is just A1, and A1 means just put a 1 into your series here. So 3 over 1 minus 3 over 2, right? I'm just going to leave it like that. S2 is A1 plus A2. You have to add up the first two terms. So it's, if you put a 1 in, 3 over 1 minus 3 over 2, plus, if you put a 2 in, you get 3 over 2 plus 3 over 3. Now what you're supposed to notice here is that the two middle terms, you have a 3 over 2 and a 3 over 2 with opposite signs, and so they go away. So when you add up the second partial sum, it's 3 over 1. There should have been a minus here, by the way, I messed up. Minus 3 over 3. And again, I could add that up, but I'm not going to. I just want to leave it like that. So if you add up S3, which is A1, A2, A3, you get 3 over 1 minus 3 over 2, 3 over 2 minus 3 over 3, 3 over 3 minus 3 over 4. Just like the previous one, some stuff cancels. So you have a minus 3 over 2 and a plus 3 over 2, a minus 3 over 3 and a plus 3 over 3. So the only term that's left is the first term that didn't cancel, the 3 over 1, and the last term that didn't cancel, the 3 over 4. Okay? Now, when you do this, I'm going to do one more. I'm not going to do it all the way. I'm going to write the answer. You can see that what's going to happen is that all of the middle terms cancel like it did right there. And so if we calculate S4, what it's going to turn out to be is 3 over 1 minus, and let's see if we can guess what it would be. So if you look at the last terms here, the first last term was 3 over 2, then 3 over 3, then 3 over 4. So what do you think this one is? How about 3 over 5, right? And S5, if you calculate it, will be 3 over 1 minus 3 over 6. And so what you do at some point is you realize what the formula is. So we realize that it works out to Sn equals 3 over 1 minus 3 over n plus 1. Now the reason it's n plus 1, right, is if you compare the number, not that number, if you compare the number here to the number here, you can plainly see that it's 1 higher, right? The 6 is 1 higher than the 5. So if this is an n, this needs to be n plus 1, so it's 1 higher. So you come up with the nth partial sum. Once you have the nth partial sum, then you can take the limit of it. So now we just try to take the limit. So try to evaluate the limit. So limit as n goes to infinity of Sn, oops, I used a capital N, which is the limit as n goes to infinity of 3 over 1 minus 3 over n plus 1, which is, now the limit as n goes to infinity of 3 over 1, right? That's just 3. And the limit as n goes to infinity over 3 over n plus 1 is 3 divided by infinity, which at this point you should know that 3 divided by infinity is simply 0. So my limit is 3. All right, so there you go. So what's that mean? So we can conclude that this series, which was 3 over n minus 3 over n plus 1, n goes from 1 to infinity, equals 3. Or you could say it converges to 3. All right. And there we go. That is how you do a telescoping series. Now, the basic idea is always going to be the same in a telescoping series, but they can add like more stuff around the numbers. So let's do one more. I'm gonna make one up. N goes from 1 to infinity of tangent. No, I don't want to do tangent. I'll do sine. Sine 1 over n minus sine 1 over n plus 1. Okay? So, you can see it's the same basic idea. So, you don't have to work too hard after you get used to these. You just go like S1 sine 1 over 1 minus sine 1 over 2. All right. S2 sine 1 over 1 minus sine 1 over 2 plus, then you plug in a 2, sine 1 over 2 minus sine 1 over 3. You notice that it is doing the telescoping thing because you have a sine 1/2 negative and a sine 1/2 positive. So you have sine 1 over 1 minus sine 1 over 3. We'll do one more. Sine 1 over 1 minus sine 1 over 2 plus sine 1/2. I should have copy pasted this. Sine 1/3 plus sine 1/3 minus sine 1/4. Okay. Cancel some stuff. The 1/2s go, the 1/3s go. You get sine 1 over 1, which is sine 1, minus sine 1/4. All right. Once you guess the pattern, you don't have to keep writing them. You guess the pattern. Pattern's going to be S capital N is sine 1 over 1 minus sine, looks like 1 over n plus 1. Okay, now we try to take the limit. Now you're not guaranteed that the limit exists, but we try to take the limit. So we want the limit as n goes to infinity of sine 1 over 1 minus sine 1 over n plus 1. So, of course, sine 1 is just sine 1. Sine, if you put infinity in, you get sine 1 over infinity. Now, let's do this, but I need to say something after we're done. So sine 1 is sine 1. Sine 1 over infinity. 1 over infinity is 0, so that's minus sine 0. So sine 1 minus sine 0 is, well, just sine 1 because sine 0 is 0. So that's my answer. So we can conclude that series sine 1 over 1 minus, no, sine 1 over n minus sine 1 over n plus 1 converges to sine 1, which is just a number. So it's not a pretty number, but it's a number. So this is what we can conclude. All right. Now, you do have to be careful. I'm not going to do one, but I do want to say be careful. The limit doesn't always exist. So like example, if you have to do the limit of, let's just change this one a little bit, say limit as n goes to infinity of, let's say, like sine n minus, or sine, let's just say it was sine 1 minus, not sine, sine n plus 1, right? So there's no 1 over n this time. If you were doing the limit as n goes to infinity, you would have sine 1 and sine infinity. But there is no sine infinity, right? It doesn't go to a particular number, right? Sine just oscillates forever out to the right. Right? Sine infinity doesn't exist because the series is just going to do that forever, oscillate between plus and minus 1. So this does not exist. It's not a number. So no limit. Okay? So just because you can write the limit like we did here for this one doesn't mean that the limit exists. You have to actually think about it, like 1 over infinity is 0, and then sine 0, is that a thing that exists? Yes. Sine infinity doesn't, though. Tangent inverse infinity does, right? But, so here's one more example. If you had to do the limit as n goes to infinity of, let's say, tan inverse 1 minus tan inverse n plus 1, something like that, you would get, well, tan inverse 1, first of all, is pi over 4, but then tan inverse infinity, you should know, is pi over 2 from the graph, right? So this is negative pi over 4 when you work that out. And that's from the graph of the inverse tangent function, which does this. It levels out at pi over 2. So this actually does have a limit, okay? And it's pi over 2. So just be aware of these issues, that you actually have to think a little bit about them, and that's why they're making you do them. They don't just automatically exist here. All right, let's talk about geometric series now. So I think in the interest of time, I'm not really going to derive it too well here. Am I? Well, yeah, I will. I'll do the quick version. So here's what a geometric series is. So a geometric series is the series from 1 to infinity of AR in minus 1. This is going to be where A and R are real numbers. Okay, that is what they are. Now, what is this series? Well, if you work it out, it's A plus AR plus AR squared plus AR cubed plus dot dot dot, right? So you always have an A and then the power of R counts up. That's what it is. Okay, now I am going to write down the answer right here so it's all in one place. But then we'll come up with what the answer is. So this series converges to AR in minus 1 converges to A over 1 minus R if the absolute value of R happens to be less than 1. Okay, that's the convergence criteria for a geometric series. Okay, so that's what you need to know. Now, let's see. Does that make sense? Let's see if it makes sense. So let's look at a series, let's say 1 to infinity. Let's just go 2, 1/2 to the n minus 1. So this series is 2 plus 2 times 1 to the 0, 2 times 1/2 to the 0, so you don't see it. 2 times 1/2, 2 times 1/2 squared, 2 times 1/2 third plus dot dot dot, which is 2 plus 1 plus 1/2 plus 1/4 plus dot dot dot. So that's what that is. And you'll notice that these are getting smaller as you go, right? Terms are getting smaller. Why did the terms get smaller? Because the R is less than 1. Because R is less than 1, when you do like the 1/2, right? When you do the 1/2, that's not legible at all. Because when you do the 1/2, 1/2 is 1/2, 1/2 squared is 1/4, 1/2 cubed is 1/8, right? That gets smaller. Now, if you look at a different example, though, let's say n goes from 1 to infinity, let's say 3. Let's do 2 over 1 to the n minus 1. Well, that one is 3 plus 3 times 2 plus 3 times 2 squared plus 3 times 2 to the 3 plus dot dot dot, which is 3 plus 6 plus 24. Wait, no, it isn't. Plus 12 plus 24 plus dot dot dot. And of course, you can see here that the terms just get bigger. When absolute value of R is bigger than 1. Now, actually, I said 1 or more. They don't get bigger if R is 1. If R was 1, it would have been 3 plus 3 plus 3 plus 3. They just don't go bigger or smaller. But they don't get smaller. And so that's what's going on here is you need the R to be less than 1. Otherwise, the terms get bigger, not smaller. Okay? And so that's why you have this criteria for whether or not the series converges. The R needs to be less than 1. Okay? Now, how would you prove that the limit was the limit? So there's kind of a sneaky way to go about it. Let's see. So quick proof. I don't know if it's a proof. I'll put it in quotes. Quick proof of the limit of a geometric series. Okay, so here's what you do. So I'm looking at this series. 1 to infinity, AR n minus 1, which we know is AR squared, dot, dot, dot. All right, write out your partial sums. We're going to do this super fast, hopefully. Write out partial sums. S1, A. S2, AR. Right? Actually, there's not really a good way to do it. So just Sn, let's jump to Sn. Sn is AR squared, dot, dot, dot. Where are we stopping? AR in minus 1. Right, that's just the formula. Right, so that's what Sn is. Now, then what you do, though, is algebra. So what you do is, I believe, this. So you go off the rails from our normal method, and we say, okay, you say, okay, so Sn is what we said, AR squared, dot, 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 AR in minus 1. But that means, and so RSn, now why are we writing R times Sn? Because I said so, right? There's not a reason for that. I'm just doing it. So if I multiply that by R, I get AR plus AR squared plus AR cubed plus dot, 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 AR to the n. Now, actually, just to be clear, the previous term is that, and then you get AR to the n. Every power of R goes, like everything gets an extra R when you multiply by R. That's easy enough. Now, why do we care? Because this lets you do this. This says, if you do this, if you do Sn, use a different color here, hold on. Sn minus RSn. What are you going to get? Well, if you think about it, you're going to get, well, you're going to have all of these minus all of these. And just like a telescoping series, stuff's going to cancel because you're going to get A plus AR squared, AR squared plus dot, 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 up to AR in minus 1. And then you end up with minus, actually, let me just make that bigger, minus AR squared plus dot, 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 AR in minus 1 plus AR to the n. That's what you get if you actually perform that calculation. But then many things will cancel. The ARs are going to cancel because it's AR minus AR. Those cancel. All the middle terms cancel. And you eventually are left simply with the first term, A, and the AR to the n. So what I have is, back to pink, I guess, I don't know. So you end up with Sn minus Rsn is A plus AR to the n. But you can factor out an Sn, like so. You can factor out an A here. Should that be plus or should that be minus? That should be minus there, shouldn't it? I was subtracting. Fix that. You can factor out an A there. So I have this. And then Sn, the nth partial sum, is A parentheses 1 minus R to the n over 1 minus R. So that's your partial sum. It's a lot of work to get it, but we got it once. Now we try to take limit. We know how to do that, right? Take limit as in to infinity. So we get the limit as n goes to infinity of A 1 minus R to the n over 1 minus R. Now there's only one n to worry about, right? This is the only place where there's an n. And so just think about that, right? If you do the limit as, let's just say, I'm doing a different limit here. N goes to infinity of, think of it. If it's like 1/2 to the n, that's like a half times a half times a half, right? Half times a half is a quarter. Half times a half times a half is an eighth, right? They get smaller and smaller, and that limit is 0. However, if you do the limit as n goes to infinity of 2 over 1 to the n, that's 2 times 2 times 2 times 2. That gets really big, it goes to infinity. And if you do the limit as n goes to infinity of 1 to the n, that is just 1. Right? So just thinking about that over here, first of all, r cannot be 1. Right? R can't be 1 because there would be a divide by 0. So r can't be 1. And then for the actual limit, there's 2 choices. So the 2 choices for the limit are, you get, well, if r is less than 1, then it'll be like this one. So you're going to get a parentheses 1 minus 0 over 1 minus r, which is a over 1 minus r, if the absolute value of r is less than 1. But the limit does not exist if r is greater than or equal to 1. And that's your formula. So that is your formula that is presented up here, right? Limit of geometric series. All right. So that was a proof, more or less, of or a derivation of the formula here, right? You put what is this limit? It's this if r is less than 1. And if r is greater than 1, then one of these other things that I wrote on the right happens, and that's bad. So there you go. That's a geometric series. Now, what can you do with it? Well, you're going to be expected to do a few things. So the first thing you're going to be expected to do is just evaluate some limits. So let's see. Find the limit. N goes from 1 to infinity of, and then, you know, to 1/3 to the n minus 1. And you're just supposed to identify the a and the r. Identify a and r. So what are they? A equals 2, r equals 1/3. And then if r is less than 1, then find the limit. So the limit's going to be right, remember you're comparing it to a over 1 minus r. That's all it is. So for us, a is 2, r is 1/3. So you have this 2 over 1 minus 1/3. You do the calculation. 2 minus 1/3 is 2/3, and then that limit happens to be 3. So that's it. Very easy. Now they will write them in more complicated ways, and so you'll have to figure it out. So like, let's say find the limit of, start at 3 to infinity. And let me say 1 over 4 to the n plus 2. No, you know what? It's 1 over 4 to the n. That's fine. Okay, now when they do something like this, you could do algebra to force it into the form of the geometric series. But it's not easy. Okay, the algebra is, kind of a pain there. Lots of like fiddly stuff to look at. So you don't want to. By far, the easiest method is if you can't tell what the limit is, then instead just write out some terms. So just erase that. Why would you? Okay. Why would you not let me erase that, but you erase the other things? All right, don't know. So by far the easiest way to go about it is just to start out writing out some terms. So what are some terms of the sequence? Well, first of all, this was supposed to be a 3. So write out some terms of the series. I keep saying series or sequence, but series. Put in a 3. 1 over 4 to the 3. Okay. Next one. 1 over 4 to the 4. 1 over 4 to the 5. ... Now that is a geometric series, but it's not written in the correct form. So what you want to do is you want to compare this to this. Compare to A1, or sorry, we're looking at a geometric series. So AR squared ... Right? And so you just want to say, well, you have that, right? That's how the terms are stacking up next to each other. What that tells you is a lot, right? This says, number 1, A is 1 over 4 to the 3, which is 1 over 64. Right? A is the first term. Just the first term. Okay. Now, how are you going to get the R? Well, what you want to realize is that if the first term is A and the second term is AR, then you can just divide the second term over the first term and get R. And you can see that basically A2 over A1 is AR over A, which is R. So you only have to divide them. So on this one, R is going to be 1 over 4 to the 4 over 1 over 4 to the 3. So it's 1 over 4 to the 4 times 4 to the 3 over 1. So it is 1/4. Now you could have actually just noticed that it's 1/4 when you look at the formula, but you can calculate it like this. And then once you have the A is 1 over 64 and the R is 1 over 4, then we can use our formula. Right, so now we use the formula. So our series is whatever it was, 1 over 4 to the n, but n started at 3, is A, which is 1 over 64, over 1 minus R, which is 1/4. So it's 1 over 64 over, looks like 3/4. Yeah, here's my calculator. That's probably really loud for you guys, sorry. 1 over 64 over 0.75, 1 over 48. Okay. So that's how you can do it if it's hard to see. Now let's look at some more. A problem that they like is repeating decimals. Repeating decimals can be written as geometric sums. How? Well, pretty simple. Just look at them. So imagine this one. Let's say, imagine 4 point, I don't know, 55555 dot dot dot, right? Which they would normally write this way, like 4.5 with a bar over the 5. Well, but think about that. 4.55555, that's actually 4, okay, plus the decimal part is you've got a 0.5, right? So that's like 0.5 plus, and then you want to get the next decimal. So that gives you the first decimal, but then the next decimal here is going to be, what's that one? It is 0.05. And then how are you going to get the third decimal? This one is going to be 0.005 plus dot dot dot. And so once you write it that way, only the part that's repeating is a geometric sum. The A in the part that I have underlined is 0.5, and the R in the part that I've underlined, remember how you get it, it's the second term over the first one, so it's 0.05 over 0.5, which is 0.1. So you could write this as 4.5 with a bar over it is 4, okay, plus the sum, well, actually, let's not even write it as a sum. Let's just write it, let's go straight to the A over 1 minus R, right? Since it's a geometric sum, you can go A over 1 minus R, right? Which is 4 plus A over 1 minus R is 0.5 over 1 minus 0.1. 4 plus 0.5 over 1 minus 0.1 is 0.9. And then if you wanted to write this as a pretty fraction, right, you could just move the decimal place over once, or you could say multiply on top by 10 and bottom on 10. Top and bottom. And you would get 4 plus just 5 over 9. And then you could add those fractions together, actually. So 4 plus 5 over 9 is, what is it? 45 over 9 plus, wait, that's not right. 36 over 9 plus 5 over 9, which is 41 over 9. Now, why do you care about doing this? Well, they're going to ask you actually to do that process. It's a little bit silly, to be honest, but you can do it. They'll ask you, they'll say, example, write as a fraction of integers. And literally they just write like 4.5 with a bar over it, and you're supposed to come up with the 41 over 9. Okay. Um, so we just did that. That's why there's no work there. Let's do, obviously, a different one. That'd be good. Like a whole problem here. Yeah, there we go. Here's a good one. Here's a good one. This is probably where we're going to stop. So, example. Write 8.28 bar over the 2 and the 8 as a fraction of integers. Exactly the same as the previous one. So let's do the work now that we know what the goal was, because you had no idea what I was doing last time, right? So remember, 8.28 is, first of all, 8. The part that doesn't repeat needs to be separated. And then the part that does repeat is 0.28, 0.0028. That's different than the last one, right? The idea is when you add these, you want the 28 and then another 28. So you need to skip, you need to have 2 zeros. You need to have 2 zeros here so that there's space for the 28 when you add them. Next one, 0.1234, and then your 28 plus ... Right? So you write it up that way. The whole thing is not geometric, but this much is geometric. So you have geometric right there. And how do you do it? Remember, the A is just the first term of the geometric part only. So the A is 0.28. The R, you can divide two terms. So 0.0028 over 0.28, which is 0.01. Now notice how this works out. Like if you have one repeating decimal, then your R is 0.1. If it's a pattern of 2, then you have 0.01. If it was a pattern of 3, it would need to be 0.001, right? That's what gives you those 2 zeros right here. Is like, that's what saves 2 zeros worth of space. All right. So anyway, you have the A and the R. So so the series is 8 plus A over 1 minus R, which is A is 0.28 over 1 minus R, which is 0.01, which is 8 plus 0.28 over 0.99. You're going to need to move the decimal place twice on top, twice on bottom. Then you need to get a common denominator. So 8 times 99 is 792 over 99 plus 28 over 99. 792 plus 28, 820 over 99. Yep, looks good. And that's what they want you to do. Now, if you look at the book's method is a little bit more complicated than what I do. Of course, I'm doing a good job and they're not. No, not really, but it's just easier to do this my way. All right, one last question and then we'll be done. So this will be different. This is just a series here. Geometric series. Converges? Question mark. -2, 8 over 7, 32 over 49, 128 over 343, ... All right. Don't think too hard. They told you it was geometric, so you don't have to worry about that. How do you do this? How do you get the A? It's the first term. It's -2. All right, awesome. How do you get the R? it's a2 over a1, which is 8 over 7 over negative 2, which is 8 over negative 14, which is, I guess, negative 4 over 7. Okay. Now, you can have negative r's, and that's fine, right? So we can say since absolute value of r is absolute value of negative 4/7 is 4/7, that's less than 1, right? That's what you need. Series converges to a over 1 minus r, and just calculate a over 1 minus r. So what are you going to get? You're going to get a over 1 minus r is a, where's a? Negative 2 over 1 minus r. R is negative 4 over 7. Now notice what happens here, right? You have a minus minus, so that's a plus. So be careful. Negative 2 over 1 plus 4 over 7, 11 over 7, I think. So then that's, negative 2 times 7 over 11. So that's negative 14 over 11. So point is, negative numbers don't mess you up. You don't need it listed in summation notation. It's perfectly fine to have it listed like this. Probably whatever method the book uses is harder to come up with the A and the R than what I did. So yeah. Oh, so we're done. I have one last comment, and that is you can actually, there is more than one way to have an A and an R for a problem. So, if I say A is negative 2 and R is negative 4 over 7, somebody else who does the problem may have a slightly different A and R, because if you change the A to something else, like let's say you said the A was 1, then the R could be modified to account for it in some cases. I don't think you could have A equals 1 on this problem, but on others. So just keep that in mind, that they're not always unique. As long as the final answer is the same, then it was okay. So, all right, I think we're done with geometric series then. And let me just double check here. And yeah, so good luck with the homework. See you in the next lecture.